is the discussion is theoretical in some extent, and some practical SPSS, how we solve the principal component analysis. That is our focus area today. So whatever, I have to use some notepad kind of things for the better understanding. So I take your permissions that I will switch off my videos, otherwise things becomes difficult to control. So let's start with the thing that is uh, 1 minute just. Whether the notepad screen is visible to all?
Yes, sir.
Yes, sir.
Okay, okay. So today our discussion is on multivariate analysis, and basically this is basically we'll focus on principal component. So first I have to discuss what is actually the multivariates. I think everyone have some social science of these kinds of background, and when you prepare a research study there, we actually try to find out some causality between the assumed hypothesis, that is which generates our dependent variables, and how the dependent variable is related with uh, your studied independent or explanatory variables. And multivariate, when you consider the multiple number of variables, specifically we faces some problems. Problems is that suppose y is your, that is output variable, and it is influenced by several independent variables like x1, x2, x3, and so on, like xk. So in case of multivariate, we are not dealing with this part. We are basically dealing with this part. In any uh, analysis like principal component or factor analysis or the cluster analysis, we are dealing with, you have to control, you have to make some control over this. What is the reason why we are dealing with this kind of variables only? Because as we know in the basic econometrics, if we consider some regression based analysis of this kind of things, then as the number of explanatory variables increases, what is happening that the explained part, that is in econometrics we call it as explained sum of square, this is going to increases, and as a result the multiple coefficient of determination or the correlations between this, which is measured by these are the basic things, by this one, that is ESS by TSS, that is explained part by total part, it actually increases. So if you address your regression by such a way that by including all such explanatory variables over the dependent variable y, I found the R square is like 0.92 or 93, this kind of things. That means you are demanding that the very high correlation between these kinds of things. But this is due to the fact that they are not fully explained why. If you increases the number of variables, automatically explain sum of square increases and R square increases. This is the basic problems of econometry, multiple regression method. These are basic problems. So we have to, and another problem is you all are aware probably, that is the multicollinearity. That means the collinearity between the variables. Collinearity between the variables. These kinds, if there are relationship between the variables, we don't know if it is then the problem is aggravated further. So to consider um, the facts like as the explanatory variable increases, the ESS increases, R square increases. That means model is good, well fitted. We say whether it is uh, it is not actually we are telling it's better way, that is it is not the thing, that is R square is not the all things. That means it is not the true representation of the regressions what we consider. So we have to so why we have to consider the factors like explanatory variables or the independent variables. This all variables are influencing the y, but not at the same rate, not equally important to us. Someone is more important, someone is less important. So to make a fittest model, it is our task in case of multivariate, that to find out those variables which are explaining correctly your dependent variables, which are important, which are more important for your model, and that we have to check. Suppose you do some socioeconomic study, you consider a dependent variable and you consider 100 independent variables. So 100 independent variables means it is very large. So all the 100 variables are not important to me. Which are most important? I have to make a list of 25 or 30 variables like this. And how we do the process, that is how we identify the process, which are more important or more significant variable to us. And today we are actually going to discuss one kind of method for the identification of such variables, and that is principal component analysis. I know that all of you are not from the background of mathematics or this kind of things, statistics, but some background work, if we don't know, it is not possible for us to explain the PCA results. It is not possible for us to understand the what actually the PCA results gives us. So statistical work, some kind of statistical work and some kind of mathematical work is very important to undermine that why it is how it is working. So in case of principal component analysis, we have to consider large number of variables first, that is large number of variables, and as well as large data set. That means you have to consider the variables are large, and as well as the informations on a particular variable are also large. So then this kind of analysis becomes quite meaningful. So if you are going to find out the principal component as per a small number of variables and small data set, it is not always meaningful. It is useful for us for large number of variables, maybe 20, 30 these kinds of variables and a large data set. That means very valuable values are over the different periods or over the different persons, so like this. So basically what principal component is doing, that is it reduces the number of variables. That means which variables are more important to us, it is identified by the PCA. So basically it is a data reduction technique. So basically it is a data reduction technique, and it is developed. It is a quite old work, that is it is developed by Harold Hotley in the year 1933. So first questions in your mind, that is when we feel the need of PCA, that comes from here, that is large number of variables and large number of data set. Now I think you know that the variance is actually what gives us variance of a variable, that actually shows the variability. And you know, the variance of, suppose, a variable x, it is defined as this way. That means if we are going to know the meaning of this part, that means how the values of xi are deviate from the mean values. So if we get a large values, that means the large value of variance, that means it is a with higher variability in compared to a variance with small value of sigma yx square. That means it is a low variability. And in case of econometric study, when you explain your dependent variable in terms of the explanatory variables, those variables are more significant to explain your model whose variability is high. So that is the important, and whose this variability over the data set is high. So when you consider a multiple number of variables, because large number of variables we assume, then we have some variance as well as covariance. Suppose x and y are the two variables, so you can find out the sigma x square and sigma y square, as well as you can find out the covariance of xy, and you know the covariance formula. So we can define the variances and covariances all in a single term. When you consider it in the form of matrix, it is called variance covariance matrix. I come to the what is the variance covariance matrix. I will come to that. So all variables are not equally important to us. We require a data reduction, and this kind of data reduction can be done by different methods. In economics, in sociology, in anthropology, we apply different methods like entropy, like topsis. These kinds of methods, they are actually also reducing the number of variables. And similarly, PCA is also a uh, data reductions process. So if we consider the case of three variables like x, y, z, suppose three variables is there, then we get the variance covariance matrix by this way, that is the covariance between x and x, covariance between x and y, covariance between x and z, and similarly the covariance between yx, covariance between yy, and covariance between yz, and similarly covariance between zx, covariance between zy, and covariance between zz. If we consider this matrix, that matrix is actually known as variance covariance matrix. And you know the covariance between the two variables, suppose I am considering x and y, what is the formula? The formula is this. X covariance between xx, between x, that will be what? 1 by bar, and also xi minus x bar by n summation of x bar whole square, and that is the variance. So if both the variable is same, the covariance generated the variance. That means it is the variance of x, it is the variance of y, and it is the variance of z. So all the diagonal values of the variance covariance, this is the variance covariance matrix. All the diagonal values of the variance covariance matrix is identify the variances of the variables. Since there are three variables, so we get a 3 by 3 matrix, and the diagonal elements are variance of x, variance of y, and variance of z. And all the off diagonal elements, these elements are the covariances. Now look at another important feature is that the covariance between x and y is same as covariance between y and x. The covariance between z and x is same as covariance between x and z. And covariance between z and y is same as covariance between y and z. So normally, if we get a matrix in terms of the data, we are right. We have to write it by this way. Suppose this is a variance covariance matrix that is 12, 21, 15, and suppose it is 20, 18, and 22. Why I am not writing this? Because these are three repetitive values will be there. So this is the covariance between x and y. This is the covariance between x and z. And this is the covariance between y and z, and this is the variance of x, this is the variance of y, this is the variance of z. So diagonal values are the variance, and the off diagonal values are showing the covariances. Okay, it is up to this. I think there is no problem. Is it okay? Am I audible to all?
Yes, sir.
Okay. So suppose there are p number of variables, and they are not, mind it, these variables x, y, and z, they are not separated in terms of whether they are dependent or independent variables. So you cannot split or distinguish the suppose there are p number of variables like x1, x2, and xp. They are not separated, and they are in terms of which one is dependent, other is independent. Like this, it is not working under the multivariate. In case of multiple regressions, we know there is some dependent and some independent. But in case of multivariate analysis like PCA, they are all are considered as the independent variables. Mind it, this is a very, very important thing to undermine. We are dealing with only the independent part. We are not dealing with anything with the dependent part. So, if you consider any one individual, and for that individual you get all the variable values of all the variables, and for another individual you get the values, and for the another individual you get the values. Suppose this is the thing. Suppose you are going to doing some city based data on pollutions, different kinds of pollutions, or these kind of things. So for a particular city you get the different levels of pollutions. So clearly, mind it, it is important that if there is a difference between multiple regression and multivariate analysis. When we split the dependent independent variables, that is the multiple regression. But if we cannot split the dependence independence variables, then we go for multivariate. And in case of multivariate, we have some special interest that which variable we have to include in our model and which variable we have not to include or exclude it from the model. So in multiple regression, one and each independent variable should have separate independent impact on the dependent variable. Mind it. In multiple regression, what is happen? That is, if we consider a regression like this, that is beta 0 plus beta 1 x1 plus beta 2 x2 plus and so on. So beta 1 is what? The impact of x1 on y, how it is, that is expressed by beta 1. Similarly, beta 2 is what? What is the impact of x2 over y, that is measured by beta 2. So each and every variable, independent variable, have some separate independent impact on the dependent variable. But in case of multivariate analysis, when you are dealing with the set of independent variables only, there is no such dependence independence kinds of things. So in multivariate, we find out the splitting of the variables by such a way that which one is more have more variation in compared to other. Variability is high for which one, that I will accept into the model. So multivariate analysis, if it is considered that independent method as independence in the sense, but that is there are a set of independent variables. So then we have some questions that what are the variables? What first we have to discuss what are the variables, and then we go for reductions of the number of variables. That can be done by factor analysis, cluster analysis, discriminating analysis, and if the observations, if the independent variables have some specific values, and if they do not have some specific values, if they are the qualitative variables, then we go to multiple discriminative scaling, multiple correspondence analysis, latent structure, like this. So these are the ways how we reduce the things like PCAs. So data in case of PCA, when you're dealing with large number of variables like this, and we have to reduce the numbers of these variables which are important for us, that means we are expressing the word as lowering the dimension. The question is, what is dimension? Two things are very important. That means you have to understand from this, that is what we are trying to do with the principal component. We are lowering the number of variables, because all variables are not important to me, which someone are important, someone are not, or less important. So we have to ignore the less important variables. We have to exclude the lesser important variables. Then that process is known as, or the way how we exclude the lesser important variables, that is means the lowering the dimensions. And another thing is important as well, as that is, in case when we are doing the things like lowering the dimensions, there is another there is the way by which we are lowering the dimension, that is known as orthogonal transformation. So the two thing is very important. I actually give you the sense that what is the proper meaning of lowering the dimension, what is the proper meaning of orthogonal transformation. But you learn these two terms. That is, these are these two terms. By these, with the help of these two terms, we are actually lowering the number of variables. And after doing these two things, what we get the more important variables and the less important, list of more important variable and the less important variables. These kind of things are known as principal component. That is, principal component shows us these are the variables with this kind of principal component. They are more significant, more important to us in compared to the others. Or what are the factor scores, what are the principal component scores of the variables when we are dealing with large number of variables. So let us start with very easy assumptions. That is, we are starting with two variables. Up to this, is it clear to all? Or if you have any questions, you may ask.
Sir, can you please explain what is the difference between multiple linear regression and multivariate
Yeah,
regression
yeah,
that you
yeah,
have?
yeah, 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 yeah. In case of, I am telling this, in case of multiple regression, you have to handle two things simultaneously, that is the output and the inputs. Okay, we have to explain how the inputs influences the output in terms of these beta coefficients. or in terms of the t values of the betas, that is whether they are significant or not, these kind of things. But we do not know that whether x1 is more important in compared to x2 to explain out. This is the main problem of the multiplication. Major problem comes from what angle? That is, if you increase the number of the explanatory variables, we know the ESS, that is the explained sum of square, increases, and as well as R square increases, and multiple R capital R square increases, and we are demanding that our model is very good, but truly that is not happening. Because why? As you increases the number of explanatory variables, your R square automatically increases. So how are you demanding that these are the important variables? This is the problem of multiple regression. So to identify whether x1 is important or x2 is important, we have to go for multivariate analysis. That means which variable is more prominent, more significant for our model, for our analysis, that is done by the in terms of their variability. Multivariate is working in terms of the variability. And basically the things is measured on the basis of Euclidean distance formula. I am coming to that. Okay. That is the difference between multiple regression and multivariate. Is it clear to you?
Yes, sir. Thank you.
Okay. Okay. So let us start these two things, that is lowering the dimensions and orthogonal transformations. We are getting then the principal component. This is the overall working of the model. The principal component is doing these three things, dealing with these three things. That is lowering the dimension is the first thing, or by how it lowers the dimensions, that is the orthogonal transformation. And after making the orthogonal transformation, we get the principal one. The software like SPSS, JAMO, VR, everything, they are working by these three mechanisms. Okay. So software operation is not a very important or significant task. If anyone who doesn't have any idea on statistics, that can be done. But explanation of the model is very important. And to make an explanation, you have to learn these background things. So suppose we are dealing with two variables, x1 and x2. And what is the data matrix? That is, suppose the data matrix is by this way. That is x11, x21, and dot dot xn1, and x12, x22, dot dot xn2. These are the observations of the two variables x1 and x2. These are the observations of x1, and these are the observations of x2, and we consider a matrix. Okay, it is. Now what we are doing, suppose we are plotting these values on an axis, on a graph paper. We are measuring x1 here, and we are measuring x2 here, and we plot all these values, that is the x matrix. And suppose the observations are like this. Suppose the points are like this. Okay, it is. I plot the data set of x1 and x2 of these combinations, and I get these points. These are the points. Now I am checking, I'm telling you that in case of principal component or multivariate, first we are dealing with what? Variability of the data set. So if I consider the variability of the data set, I first check what is the variability of x1. We know this is the positive side of x1, and this is the negative side of x1, and this is the positive side of x2, and this is the negative side of x2. So how much x1 is positively varied? That is, what is the maximum values of x1 in the positive side? I consider this is the point which shows the highest x1 values, highest positive x1 values, this points. And here it is the point where I find out that the minimum values of x1. So I draw two vertical lines through these 2 points. This is the lowest value of x1, and this is the highest value of x2. That means x mean, you may term it as x mean and x max. x1 mean and x1 max. These two are the values. So if I make simple without any mathematics, if I make the difference of these two, that is the distance. Okay, it is. That is the distance which is showing us that what is the variability of x1. Clear it is? Is it clear to everyone?
Yes.
Okay. Now, similarly, I'm considering the x2, and suppose this point is the highest point of the x2 and this is the lowest point of the x2, and I draw two horizontal lines to these points, and the distance between these two lines, that is showing the variability of x2. So look at the figure, look at the two distance part. This is the variability of x1 and this is the variability of x2. So from the data set X, I get the ideas that at what level the variability is. I find out the values of the variability, and in statistics, when we measure such variability of x1, that is identified as variance, and that is what 1 by n summation of x1I minus x1 bar whole square. I is equal to from 1 to n, and s22, that is this is 2, 1 by n summation x2I minus x2 bar whole square. So these are the variances. That is the statistics express how the data sets are variable. That is in terms of S11 and S22. And mathematics or geometry express the variability by this way, that is the measuring amount of distance. But here, from this thing, we cannot get the that is how they are variable. Rather, statistics gives us further idea, like that is covariance of X. If we consider the covariance of X matrix, that is S11, S12, S21, and S22. And you know, this is the S11 and S22. These are these values, these two values. That is S11 and S22. And what is covariance of X? This is S12 or S21, and that covariance, that is S12 or S21, both are same. This is measured by 1 by n, or some books it is written as n minus 1. That is x1I minus x1 bar and x2I minus x2 bar. These are the variance covariance. And similarly, if we consider the correlation matrix, that is correlation matrix of X, if I divided this covariance by variance of X and variance of Y, this covariance matrix, then it becomes 1, then it becomes R12, this is becomes R21, and this becomes 1. That is the correlation matrix, which is generated directly from the covariance variance covariance matrix. And you know what is R12 or R21? That is what? That is S12 by root over of S11 and S22. You know that. This is the R12 and R21. Because these two are equal. Now, in the figure, look, in the above discussed figure, what I am doing, that I am just removing this. I'm just removing this. This is the data set originally. Now, what I am doing, that this x1 axis, actually I what I get from here in this diagram, that I measure the variability in graphically, and that variability can be expressed by statistically in terms of variance covariance or correlation matrix. Now what I am doing, this x1 axis, suppose this x1 and x2 were the two axes, you can consider these two as a stick, and the crossing of the stick is bind by some stitch or this kind of things. Now I am rotate this axis anti-clockwise and by angle theta. Suppose after the rotation, the axis becomes like this. Okay, this rotated axis, this rotated two axis, suppose I write it as a Z1 and this as a Z2. And how Z1, Z2 comes? This comes, that is, I rotate this axis by angle theta. Suppose by some angle, I rotate the axis and I get this. Now I am going to measure the level of variations again of the two variables x1 and x2. And what I get, that is highest value of x1 is distance is here and lowest value of x1 distance is here. So what is the variability of x? This is the variability of x. And what is the highest value of x2? That is here. And what is the lowest value of x2? This is here. So what is the variability of x2? This is the variability. So in terms, when I rotate the axis anti-clockwise by some angle theta, we find out that the variability of x2 is more higher in compared to, sorry, variability of x1 is much higher in compared to the variability of x2. So if someone asks me, that is between these two variables, x1 and x2, which one you will opt to for your model, I obviously said that x1 is much more variability in compared to x2, so I have to opt for x2. Is it clear to all? This is the basic things. Or I can go further. I can repeat it again. If you have some query or questions, you can ask. What I am doing, I am just the data set original. Look at the original black colored axis, and the data set looks like this. That is this oval shape data, and I rotate the axis by angle theta, and the new axes are given by the red lines, but I rename the axis because these are not Z x1 and x2. So I have to rename this because after on x1 some theta degree rotation is we actually done. So it is not possible for us to take the problem that is it is remains same as the variables are not remains the same. Variables are actually changing. What I'm going to say, the variables are x1 and x2 was the earlier variable. Now it is written as Z1 and Z2 because Z1 and Z2 are related with x1 and x2, but not Z1 means x1, not Z2 means x2. Z1 is dealt with some combinations of x1 and x2, and Z2 is also expressed as some combinations of x1 and x2 after such theta degree rotations. And we find out by the same way like before, that is the variability of x1, which is measured by this distance, is quite higher in compared to the variability of x2 in our open eyes. So we can say that x1 is more variability in compared to x2. So if anyone asks which variable you have to choose, whether x1 or x2, then we can say we have to choose x1, not x2. Is it clear to all?
So by variability in the data, we try to say variance. If we say
Pa-
variance in the data, we are actually trying that's denoted by variance. So,
Pardon, I'm not getting you. You just
uh,
repeat your question.
I'm just asking, as you were saying, that variation in the data or variability in the data, and
Yeah,
we should take that data which has more variation because our model gets fit more. It gets more fitter. So
yeah,
that by variability, so we are trying to denote variance. So,
yeah.
achha, thank you. And this
Okay.
rotation is done just to see which variables have more variations. So we will take that.
Exactly. And the software in SPSS or in R or in EViews or anything, they are doing this rotation behind the screen, and they will, after such rotation, they will give you the idea that which one has the greater variability.
Okay.
This is the why I am doing this, because to give you the that is the flavor that what actually the principal component means. These are these Z1 and Z2. I am saying it. I'm coming to that factor how Z1 Z2 formed. I'll come to that little bit of mathematics, because if someone have some that is disliking in favor of mathematics, you have to bear this. It's but these Z1, Z2 are the new principal components. And we found that Z1 we have to accept Z1, not Z2, because its variability is high. Is it okay?
Yes.
So, actually what is happened, I am not going to that mathematical derivation. I just give you the sense, that is, consider the figure again. That is, this is the x1 and x2, and these are the, suppose this is the Z1 and Z2 after making the rotation. And suppose a point which is here, the name of the point is M. So in terms of the original variable, that is x1 and x2, what is the contribution of x1? This is the contribution of x1, and this is the contribution of x2. That means this distance is the x2 and this distance of the x1 of this ordinate. Now, when I consider the rotation, what is happening? Look, I'm just erase some part, otherwise it will just. What is happening? When I am considering the situation of M, which originally, suppose this point is M4. Suppose this point is M4 and this point is M2. Suppose. Now, what is happening when I rotate this axis, that is in terms of Z1 and in terms of Z2, how we consider, how we look about the M points? We look about the M points from these two intersections. That is, what are the intersections? That is, when it is intersect the x1 at M4 points and x2 at M2 points, we have to draw the perpendiculars on Z1 and we have to perpendiculars on Z2. And the angle between these two is theta. The angle is between these two is theta. So this point, in terms of what is the point? Original point is M. Now what I'm telling you, that from this point you have to draw a perpendicular on this axis and also a perpendicular on this axis, and from here you have to draw a perpendicular on this axis and you have to draw a perpendicular on this axis. That is these points and these points are expressed in terms of Z1. This point is expressed in terms of Z1, this one and this one, and this points M2 is expressed in terms of Z2. So look at the situation of M2 and M4, or whatever may be the name. It becomes a combination of x1 and x2. Now Z1 is expressed as a combination of x1 and x2, and similarly Z2 is expressed as a combination of x1. What kind of combination? Actually, in mathematical form, these combinations are Z1 combinations is written as x1 cos theta and x2 sin theta after theta degree rotation, and Z2 looks like minus x1 sin theta and x2 cos theta. So these are the looking of Z1 and Z2 by making, after some making theta degree rotation, what actually the Z1 gives us and what actually the Z2 gives us. That is, look, it is the combination of x1 and x2. It is the combination of x1 and, sorry, this is x2, and it is the combination of x2. So z1 is this, z1 is this, and z2 is this. z1 is what? X1 cos theta and x2 sin theta. And z2 is what? Minus x1 sin theta and x2 cos theta. This, how we get this? This is a purely a trigonometrical work and coordinate geometrical work. I'm not telling you that you have to know how these are comes, but actually these are the formulas by which we get the z1 and z2. You need not require to remind these formulas, but I'm for the better functioning of the mathematical things, I am just showing you. So in vector matrix notations, we can write this z1 z2 by this way, that is z1 z2 is equal to cos theta sin theta and minus sin theta cos theta and x1 x2. That is, you know better, that is what is z1, that is this 2 multiplied by this, then we get this z1. And what is z2? That means this multiplied by this, you get the z. So this is the way we can transform the axis, transform the point M in terms of the z1 and z2. That is, in terms of the x1 and x2 combinations, we can express z1 and z2 by this way. And in vector matrix notation, this z1 and z2, we have to written this z1 z2, this thing, that is this part. Actually in vector matrix notation, this is written as z is equal to A transpose x. What is A transpose? A transpose is this part, that is cos theta sin theta minus sin theta cos theta. This is the A transpose. And so what is A? A is just transpose of these two, that means cos theta, this two, that is cos theta sin theta, written as by this way, and sin minus sin theta cos theta is written by this way. This is the original A, and its transpose is this. And this factor, that is cos theta sin theta, and this factor minus sin theta cos theta, are known as, suppose, A1 and A2. So if they are known as A1 and A2, matrix, this is the matrix, and first column of the matrix is known as A1, second column of the matrix is known as A2. So when we are dealing with data in our practical life, in our practical example like PCA, this A matrix, we can write it not in terms of theta or this kind of things. We write it in terms of A1 to 1 1, A1 to, these are the values, and A2 1 and A2 2. And this is the A1 and this is the A2. And what is, if you compare, what is A11? A11 is actually the cos theta. A21, those who are interested in that is mathematical background of this is the minus sin theta. A12 is sin theta, and A22 is cos. Sorry, this will be the cos. This is the cos theta. So by this way, but this is not required for all of you. Those are the researchers in science, in social science. So what I'm going to, but interesting result is this, that is, if you do not have any flavor of this mathematics, you will not get that what actually PCA means. Now look, what is A1? That is, this part is, I am telling this part is A1. So A1 is what? Cos theta sin theta. And what is A2? A2 is this, minus sin theta and cos theta. So A1 transpose, look at the factor, A1 transpose A1, if I make it, that means if I make the transpose of this matrix, it becomes cos theta sin theta into A1, that is cos theta sin theta. Look the beauty of the model. If we multiply these two, that means cos theta, it is cos square theta, and sin theta, it is sin square theta, and the things becomes 1. Similarly, A2 transpose A2, that is also equals to 1. That is also equals to 1. Not only this, what is the thing, that if I consider the whole model, that is, if this is A transpose and this is A, if we consider this is A transpose, this is A. Now look at the factor, that is A transpose A. So what is A transpose? that is cos theta sin theta and minus sin theta cos theta. And what is A? That is cos theta minus sin theta and sin theta cos theta. And that is actually, look, first element will be what? Multiplication of these two. That means cos square theta sin square theta, that is 1. If we multiply these two, second element is what? This one into this one, that is called minus cos theta sin theta and sin theta cos theta, so it will be 0. And again this element will be what? This multiplied by this, that is minus sin theta cos theta and cos theta sin theta, that is also 0. And this into this, that is minus sin theta, that is sin square theta, and cos theta that is cos square theta. This is 1. That means this is an identity matrix. So not only for A1, each and element wise multiplications, A1 transpose A1, this is 1. A2 transpose A2, this is 1. A transpose A, the full matrix, that is an identity matrix. So A is a symmetric matrix by which A transpose A is identity matrix, and it is considered as orthogonal. When such kind of things is happening, then we call it such kind of transformations. That means what we make, that is by transforming this axis, but we get the Z1 and Z2. For such Z1 Z2, that is Z1 is what? Z is what? That is A transpose X. And what is the property of A transpose matrix? We get that the each and a column of the each column of the A matrix, the capital A matrix, that is A1 transpose A1, that is 1. A2 transpose A2, that is 1. And not only that, full the transform, that is A transpose A, that is also 1. That is also an identity matrix. So this is called the orthogonality. So first we are learning about what is the meaning of the lowering the dimensions, that is by which from the first figure we find out that we can say that the variability of x1 is higher in compared to the x2. And next thing we are getting that after lowering the dimensions, what we are getting, that is about the A matrix, that about the data matrix, that the new data matrix A has some property that it is orthogonal. So why in the initial part I am telling you that the two things are very important in case of principal component, that is the lowering the dimension as well as the orthogonality. So here we consider the number of variables is 2. So if we consider that the number of variables is rather higher, then that A transpose matrix is look like this. Suppose A11, A12, and dot 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 A1P, A21, A22, dot 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 A2P, and so on, AP1, AP2, and dot 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 APP. If this is a matrix where the variables are like this, x1, x2, and dot dot xp, if there are p number of variables, then after making, look, when I am making the transformations, when I'm making in case of two variables the transformations, we get the two principal component like z1 and z2. So when I'm making the p number of variables in the model, that is x1, x2, xp, and we get the transpose matrix, then we get the p number of principal components. And what are the principal components? That is z1. If I consider the first principal component, that is a1 transpose x. That means what? A11 x1 plus a12 x2 plus dot dot a1p xp, and z2, that is what? A2 transpose x, that is A21 x1, A22 x2, and so on, A2p xp. And by this way, for each and every variables, that is by this way, for p number of variables zp, that is AP transpose x, that is AP1 x1 plus AP2 x2, and so on, APP xp. So there are p number of principal components we get, and as per the variability, this is the first principal component. First principal component, this is the second principal component. By this way, is the pth principal component. When we run these things in SPSS or in views or in any software, they will arrange, gives us the result by this way, that Z1, this Z1 is the first principal component, which shows the highest or maximum variability among all ZJs. That means whatever the number of ZJ will be created, among them, Z1 shows the highest number of variability, maximum number of variability. Similarly, Z2 gives us the second principal component, which is the next maximum variability among other all ZJs. And Z3 by this way, that is the third, that is again the third principal component, that is the next maximum variability. Here J is what in the first case, when you write about the first case, J is what? J is 2, 3, 4, 5 by this way P. In the second case, when you write, it is from the 3, 4, 5 and so on P. In the third case, when you write, it is 4, 5 and so. So for each and every principal component, looks, we are not considering the earlier one. So all these principal components are derived among, we can simply say that the variability of Z1 is greater than or equal to variability of Z2, is greater than equals to variability of Z3, is greater than equals to so on variability of Z4, ZP. So this is the principle behind which the principal component thinks is this. For example, I'm giving you an example. That is the Z1. That is the first. You will get the results by this way from the software. Z1, that is the first principal component. Suppose it explains 66.66% variability of the data matrix. Z2, that is the second principal component, which suppose 23.22% variability of the data matrix. Z3, that is suppose by this way the result will come, that is 5.05% variability of the data matrix. And Z4, that is the third principal component, that is 1.25% of the variability of it. So you can find out that this, among these four principal components, Z1, Z2, Z3, only the three variables, that is these three principal components, explain majority of the variation of the data matrix. So by this way, for higher number of variables, we can say that this variability is explained by what number of variables we can choose them. So this is the way how the principal component is working. Okay, it is, or I just give you the sense that is how it is working. If there is any questions or anything, any kind of you don't consider those calculations like cos theta, sin theta. You just try to get the essence of the things. So in case of principal components, we have to find out that A transpose X. We have to get calculation of A transpose X matrix of the data set. A transpose is what? That is, the transformed value of the data matrix. So then it will generate us which variable have the highest variability, which variable is the next highest variability, which variable have the after that. So by this way, we will get the variability. And what is the thing that the thing is that the variability, that is variance of any principal component, that is ZJ. This is defined by variances of, that is suppose AJ transpose X matrix. And I think if you have some experience to deal with econometrics in terms of matrix notations, this variance is actually, we have to write this by AJ transpose S AJ. This S is the variance covariance matrix. And we are doing what? We are doing the maximization of this variance. We are doing what? Where the variance is maximized. And subjective condition is what? Subjective condition is orthogonality. That is what? That is A transpose J. This is equals to 1. Or you may write it by some books. It has written this by this condition. That is, it is equals to 0. AJ transpose minus AJ is. So we are going to maximize this. That means the variance. Which variance is maximum? The software like SPSS, they are working the thing in the background. They are changing the dimensions. Then they are making the orthogonality by such a principle, that is maximization of the variance subject to this constraint. That is AJ transpose AJ minus 1 is equal to 0. And those who are background from economics or anywhere, they know the maximization principle. That is, they can use the Lagrangian method and get the solutions like this. That is S minus lambda I. This multiplied by AJ. I'm not telling you everyone that is to follow these mathematical things from where it get, but those who are from the mathematics or physics background or economics background, they know the Lagrangian principles, and from that Lagrangian principles we get the solutions like this. That is S minus lambda I into AJ equals to 0, which actually generates the principal components. And the important thing is this, that is the variance covariance matrix minus lambda into I, where lambdas are this equals to 0 because AGIs are not equals to 0. And this actually gives us the eigenvector or the characteristics equations from where the general characteristics roots follows, and that gives us the eigenvectors. I am just, those who are not understand these kinds of languages like eigenvectors, eigenvalues, I can give you a very simple example to understand the what actually I am going to say. Suppose I have two variables. I'm giving you some practical examples. Suppose we are dealing with two variables. One is profit, another is sales. And very simple, we are dealing with 12 number of observations. What are the observations? I am writing you the observations, that the observations of the X matrix values are like this. The amount of profits are this: 10, 12, 11, 9, 9, 10, 11, 12, 11, 10, 11, and 12. Suppose these are the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are the 12 months profits of a particular company. And the sales values are like this: 100, 110, 105, 194, 95, 99, 104, 108, 105, 98, 103, and 110. These are the sales value of the 12 days, suppose. So what is our data matrix? My data matrix is, if I have to write it in the column form, this is in the that is by this way, that is 10, 12, 11 by this way, 11, 12, and here it is 100, 110, and 105 by this way. This is 103 and 110. This is my data matrix. This is the profit and this is the sales. These two values. So we are going to extract the PCA. So you get the data set. This is suppose you can consider this is suppose x1 and this is suppose x2. So you can calculate the variance of x, and you can calculate the variance of variance of x1, and you can calculate the variance of x2, and you can find out the covariance between x1 and x2. So we get the covariance matrix. So we get the covariance matrix. This is the data set. Suppose this is the data matrix, and we get the covariance matrix. And suppose if we calculate the variance and these things, I am already calculated, so I write the values. So these are the variance covariance matrix. So you can get that this is the variance of profit, and this is the variance of sales, and this is the covariance. These two are the covariance between profit and sales. Okay, is it clear to everyone of this example?
Yes.
Okay. So now what I am going to calculate, I am just telling you, you have to remind this equation. That is, we have to find out that S minus lambda I. So what is S? S is this one. S is this, that is 1.15, 5.26, 5.26, and 29.4. And I is what? We know it is an identity matrix. So what is S minus lambda I? That is 1.15, 5.26, 5.26, and 29.54 minus lambda into I is what? 1001. So that is equals to 0, because the condition is this. You just remind S minus lambda I equals to 0. So this equals to 0. Now it gives us, by the matrix subtraction process, it gives us 1.15 minus lambda, because lambda is multiplied with 1, lambda is multiplied with this 0, it is 0, lambda is multiplied with 0 is 0, and lambda is multiplied with 1 is lambda. And making the subtraction, it becomes a new matrix like this. This equals to 0. And we know the solution of this is 1.15 minus lambda into 29.54, because cross multiplication it is determinant's value, that is 29.54 minus lambda minus 5.26 square. This equals to 0, because 5.26 into 5.26 is square. And if you solve this equation, you get the result like this, that is 33.971 minus 30.69 lambda plus lambda square minus 33.1776 is equal to 0. And if we rewrite it, it can be written as lambda square minus 30.69 lambda plus 0.7934. This is the quadratic equation, and you can solve the quadratic equation, and you get the value of two values of the lambda. Suppose the values are lambda 1 and lambda 2. These two values becomes, by the formula of Subhasis, that is 30.69 plus minus 30.69 b square minus 4ac, 4 into 1 into c is 0.7934 divided by 2a, that is a is 1, and we get the values like 30.66 and 0.03. This is the value of lambda 1, and this is the value of lambda 2. So we get the two eigenvalues. These are called the eigenvalues, or that is the values of the lambda, and we get these two values. So look, if we consider the first, what we get the first eigenvalues, that is 30.66. What we get the second eigenvalues, that is 0.03. Now, if we get the first eigenvalues, the things becomes, if I put this value of lambda here, that is in this form, that is 30.66. If we put it here, then the things becomes 1.15, 5.76, 5.76, and 29.54 minus 30.66 into 1001. This whole into A1 equals to 0, where what is A1? You remind this earlier, that is, it considers of two components. Since we are dealing with the two variables, it is considered with A11 and A12. So if I put the value of A1 instead of this A1, if I put it here A11 and A21, then solving this system, you can get one equation, that is solving this system, you can get the equation that is actually looks like 29 minus 29.751, 29.51, 5.7 into A11, A to 0, and solving this we get the two equation minus 29.51 A11 plus 5.76 A12, this is equals to 0, and 5.76 A11 minus 1.12 A12, this is equals to 0. From this two equation we cannot get the unique solution because both equals to 0. So we have to use another formula, that is the orthogonality condition, and that is what A1 transpose A1 is equal to 1. Now A1 transpose A1 means what? A1 is this, A11, A12, and A1 transpose is what? A11, A12, this equals to 1. That means A11 square plus A12 square, this is equals to 1. And that actually means A12 is nothing but root over 1 minus A11 square. So if I put here in place of A11 or in place of A12, that is 1 minus A11, in place of A12, if I put 1 minus
Sir,
A11
I
square.
can't hear you.
Yeah, hello. If anyone have any problem, am I audible?
Yes, sir. Yes, sir.
So if I put this value of A12 in this equation or in these equations, then we can get the value of A11. And similarly, if we have to if we go to solve this, look at this value, that is if we put the values here, that is minus 29.51 into A11 plus 5.76 into this is 1 minus A11 square is equal to 0. Then if we transfer this into that side and making square, we can get the value of A11, and that value will be, that A11 will be 0.19. If you have, if you can do solve it easily. And similarly, so if we get the A11, you put the value of A11 square here, then you get the A12, and that A12 will be 0.98. And these are called the factor loadings. These are called the factor loadings. It will come into the SPSS output. So why I am going to solve you? This is some kind of boring, but you have to learn this. That is why these are the meaningful. This will come into your output. When I am going to the SPSS, that I will show you that this will come to your output. Similarly, from the second equation, if you put again, that is A12 is equal to 1 minus A1 square here, then from that equation you get another two components. So here, for the first principal component, this is the first principal loading, factor loading, and for the second one is this. So we can write the first principal component by this way, that is first factor loadings is 0.19x1 plus 0.98x2. And similarly, if you solve the same system here from this equation, that is if you put the values of A12, that is root over 1 minus A1 square here, then from this equation you can solve the value of A11, that is just the reverse, and that is 0.98x1, and this will be minus 0.19x2. Here accidentally the values are just the reverse, but it is not the thing. So we get finally the principal components. There is the Z1 and Z2. And also the PCA helps us to find out that which is with greater variability. So model adequacy is an important factor. Before going to the software, I'm just give you the important thing. That is model adequacy is an important factor. So we get the eigenvalues, we get the two eigenvalues, that is lambda 1, you just recall, that is 30.66, and lambda 2 is 0.03. So look, the values, summation of lambda, that is sum of these two values is 30.69, and from these two values, that is if you can, we can say that look at the variance covariance matrix earlier. That is, the variance covariance matrix is what? This is my variance covariance matrix. This is my variance covariance matrix. 1.15 and 5.26 and 5.26 and 29.54. So look at the variance covariance matrix for the model adequacy. That is, variance covariance matrix is looks like this: 1.15, 5.76, and 5.76, and 29.54. So if we add the values of the variances, that is 1.15 plus 29.54, look, what is the value? That is 30.69. That means it is the summation of lambda. And the diagonal sum of the diagonal, we can call it trace. So trace of S, the traces of the matrix, is gives us what? These are actually gives us the sum of the eigenvalues. So we can say that if these traces are equals to the things, that is summation of the lambdas, all lambdas, then we can call that the model is adequate. So in this data set, if we write the maximizations results, that is if we consider the whole results in the form of the maximizations, if we write, that is A transpose S A, if this is the basic form, then what is the first, for the first factor loadings are 0.19 and 0.98, and what is S? That is 1.15, 5.76, and 5.76, and 29.54, and what is the A transpose A? That is 0.19 and 0.98. This will give you the first lambda 1, this value. That is, if you solve this in terms of the matrix by after multiplication of this kind of things, you get this is 30.66. If this thing has happened, then you can say the model is adequate. Now the question is, that is, there are some tests to after getting the principal component results, and there's some kind of test. So for example, if you go to the if you one result is Bartlett's sphericity test, I will come to that. In SPSS is showing the Bartlett's sphericity test. So look, if the data set are plotted by this way, that is in the form of the circle, then if you change the axis, the distance will remain same. The distance, the variability remains same. So it is difficult for us to find out the proper principal component. So to check this kind of things, that is whether it is possible for us to run the proper PCA or not, then you have to consider the Bartlett's sphericity test. So now I will stop the theoretical kind of discussions. So just 1 minute. So I will stop sharing, and I will join from my desktop uh, to show you that how SPSS, through the SPSS, this kind of things we are doing. Just 1 minute. You have to wait. Just 1 minute. So, Bill, I think the screen is visible to all.
Yes, sir.
So,
Yeah, yeah. That is a simple Excel where the actual data are. Look at the data. These are the data of all 2,500 near about villages of a district of West Bengal where I'm actually working, that is Purulia, and the data set is from a very well-known platform, that is the DCHB. DCHB websites, you can get the you can access the data, and these are the socio-economic profiles, and there are the 24 variables. There are the 24 variables which are actually here. So you can get the information of the data. That is, first variable is the livable conditions of the residents, and livable of residents and other use, concrete material of roof, like this. These are the separate variables, and these are the percentage form of data. So these are the number of variables. That is the villages, and the name of the villages are here. So I directly, I'm not going to that factor. That is, when I transfer this data, 1 minute just. Yeah. When I transfer this data into the SPSS data view, it looks like the variables are start from variable number 1 is not important. That is these are the name of the villages, and all other variables are showing you. That is, these are the variables. There are the 24 variables, that is running from 2 to 25, and all these variables what actually I'm already showing you in Excel. These are transformed into the SPSS. And now you have to do the principal component analysis. So this is a very simple task, and you have to just follow uh, some steps that how you get the results. So first you go to analyze. Here everyone look at the do you get that what the analyze is? What the analyze? First you have to go into the, am I audible to all?
Yes, sir.
Okay. You first go to the analyze part, and then you go to the dimension reduction part. That what I'm telling you, that the dimension reduction. And then you go for factor analysis. That means we are going to analyze the factors, and you have to click on it. Then the one window will open, and where you have to select the variables. Since the variable 1 is the name of the villages, we do not have to consider this. So you have to select all other remaining 25 variables and transform them into our selections. So then you look very carefully that these things gives us some significant significant part of our analysis. That is the factors like the things like descriptives, extractions, rotations, scores, and options. And the mathematical thing, what I am telling you, these are the uh, related uh, with these kinds of functions. So first go to the descriptives. So when you click to the descriptives, the things like univariate descriptive and initial solution is there, and you have to select only one thing, that is from the correlation matrix. That is in the lower part, you see it is the correlation matrix. So you have to find out the KMO and Barlett's test of sphericity. That means we, in this part, we are actually taking the variability part, that is lowering the dimension part. That means sphericity, that means what is the shape of the data set, and we have to find out the linear distance from one highest value of a particular variable to the lowest value of a particular variable, find out the distance. By this way, for each and every variables, they are calculating it. It is Kaiser-Meyer-Oaklin test and the Barley's sphericity test. So this is very important. So you have to, in case of descriptives, you only check the box, that is the KMO and Bartlett test of sphericity. So you make the continue. So is it clear to everyone what we are doing? I am repeating the steps again. You go to the analyze, then you go to the dimension reduction, then you choose the factors, then a new window will open. From there, you go to the first descriptives, you click on the descriptives, and then initial solution is automatically accepted by the SPSS, and you have to check only on KMO Barlett's test for sphericity. And what is the purpose of KMO Barlett's test of sphericity? I am telling you by that diagram, that is dimension, by changing the dimension of the axis, we are measuring the variability of the variables. So it is okay. I am continuing it. Then go to the extraction. When I am going to the extraction part, it is in the SPSS. It is automatically the principal components. We have to extract the principal components, that is already here. And the rotated and unrotated fact correlation matrix is automatically chosen, and unrotated factor solutions are there, and you have to choose one thing. I am not telling you up to this, that is the scree plot. This is actually gives you the directions, that is how many factors you have to choose. That means you have to consider up to what number of factors. So scree plot is, we have to tick on the scree plot. This is the first analyze part, work is done. That is correlation principal component is automatically taken by the SPSS, and the correlation matrix, it is automatically derived, and the unrotated factor solutions is also, but you have to choose whether you are interested to find out the scree plot, because scree plot is a visible solutions of how many factors you are actually chosen, how many factors you have to be considered from that kinds of plot. And that plotting, that is how many factors we have to choose, what variability, up to what level of variability of the variances we have to consider, that is based on the eigenvalues, and that eigenvalues will be greater than 1. So here they are based on the eigenvalues, and we choose the value. Automatically also automatically choose that is eigenvalue is greater than 1. So these things you have to make only in case of diagnostic, that is that you have to choose the scree plot, and everything will be automatically taken. Then we click on continue. So it is the extraction is done. Then we go to the rotation part. So in case of rotations, there are the things like varimax, quadrimax, equimax. So you have to choose, you just remind that you have to choose the varimax. When you choose the varimax, that in the display, the rotated solutions will be automatically come out, and you have to, in this factor, that is in case of rotations, it is very important to you that we are maximizing the variances. So we follow the varimax principle, and we are displaying what actually display to us, that is the rotated solutions, and we make the continue. So this is the part of rotations. Okay, it is. And in the scores part, we consider the regression technique among to find out the scores, and the only you have to save as the variables. You click on the save as the variables, and it will automatically method is the regression, and you can do the continue. And for the options, that is uh, excluded the case likewise, excluded the case pairwise, replaced with the mean. We consider the excluded case likewise, and sorted by size. Then sorted by size means what? So sorted by size means it is actually based on the choice of the eigenvalues. That is what are the highest eigenvalues that will come into the top by this way. That means they will what I am written earlier, that is variance of Z greater than equals to variance of Z1 is greater than equals to variance of Z2 by this way. So they will show the results by this way, and then we make it continue. So everything is done. So you have to find out what is the descriptives, then extractions, then rotations, then scores, and then options. So these are the simple steps to get the PCA results. Now it is okay. I click on the OK, and the results will be displayed in an output as an output in the factor analysis or the principal component analysis. So look, first output table, that is the KMO and Bartlett test. And here the Kaiser-Meyer-Oakley measures of sample adequacy is 0.905. This is a very important thing. I am telling you that KMO values, there are some remarks about the KMO values. That is, if it is below the value of 0.5, this is not acceptable. You can never run the PCA kinds of things if you find out the KMO values is below or something like below the, you can consider that below 0.6 is 0.07. If it is below 0.7, then it is give a signal to you that PCA is not give you a meaningful results. If it is above 0.9 and above, then it is a very good thing that you can your PCA you choose the PCA correctly for the data set. If it is in between 0.8 and 0.9, then it gives you the meritorious level. And if it is 0.7 and 0.8, that is gives us, it is some middle level test. So I am suggesting you that when you are running PCA, when you are doing PCA, if the value of the KMO sample adequacy is above 0.8, then you can do then you can go further. It's okay. But if it is below 0.8 or 0.7 rather, then you have some questions to face that the KMO is not acceptable. So you cannot run the principal components. Look how it has happened here in our example. What I am considering, the number of variables are 24, that is quite large, and the data set that is for the 2460, this kind of things, this number of villages, that is 2460 villages. So huge data set it is. As a result, automatically it gives us the sample adequacy is 9.05. And the Barless test of sphericity, it is a chi-square test. I'm not going to that statistical things. It is a chi-square test, and it shows the significant level is less than 0.005. That is here 0.000. That means the Barless test of sphericity gives us the significant things. That means the null hypothesis. That means no principle. What is the null hypothesis for the Barless sphericity test? That is no principle. There all variables are equally variable, with have some equal variability. That is, you cannot differentiate the variables in terms of their variability. If this is the null hypothesis, so it is rejected. That is because why the chi-square gives us that the values is significant. That means the it is rejected the null hypothesis that all variables have the equal variability. That means variability is different. So this is the first step to you. That is that gives you the that is whether the PCA, whether you can proceed with PCA or not. This first table gives you the signal. Okay. Now the communalities. What is the communalities? Communality shows, that is, the percentage of variance explained by the extracted components. That is variable. How many variables are there? From variable 2 to variable 25. So each of them at what level their variances extracted by the components, that is given to us. So the initially this is 1, because when we include into the model, what we assume that variable 2, variable 3, variable 4, these all are equally important to us. But after making the these kinds of transformations of the model, it gives us that variable 2 is explain the 62.6% variability of variability which is done by the extracted components. So here look that the variable 9 is very poor, that is 0.120. So by this way, from here, from this communalities table, you can find out, you can get that the which variable have some percentage of variances with have some greater percentage of variances which are explained by the extracted components. Now we come to the next table, that is the variance explained. So look here, there are the three kinds of results. That is, one is on the basis of initial eigenvalues, another is extraction sum of the square loadings. What are these kinds of solutions gives us? I will give you the things. That is, look, the first component, you find out that how many components are there where the eigenvalues are greater than 1. This is a very important. What I am considering earlier, that is, when I am doing the PCA, I consider my assumption is that eigenvalues level will be the variables which are important for us with eigenvalues greater than 1. I make some assumptions. So here, only the 6 variables among the 24 gives us that their eigenvalues are greater than 1. Look at the first component, only the 6, only the not 6 variables, 6 components which have the eigenvalues greater than 1. For example, the first components, its eigenvalues is 7.046, and it explains the its variance explain 29.358 of the data set of the data matrix. Second variable, its value is 1.720, and it explains 7.166%. By this way, When you come to the 7th, its value becomes 0.992 and it explains 4.135 by this way. So in this first eigenvalue, initial eigenvalues columns, you find out, you get that the 6 components are with some eigenvalues, greater than 1. So the extraction of the sum of squared loadings showing you this part showing you that only the 6 variable, only the 6 components are important for you. These are the components which are important for you. So, and their percentage of variance and that is their percentage of variance and the cumulative percentage of variance. Now the scree plot. Scree plot is what? Here in the vertical axis we are measuring the eigenvalues, and in the horizontal axis we are measuring the components. So look, in the earlier table, why it is happening so? Okay, only the 6 components have some eigenvalues greater than 1, and the 7th component eigenvalues is 0.992. Here, look at this. The 6 component eigenvalues are greater than 1, and the 7th component eigenvalues is 0.992. So in between these two values, there is one is lying between these two values. So in the scree plot, when I'm going to the scree plot, look up to the 6 components and between 7 components. If we draw a line which is parallel with the 1 values, that means from here, if we draw a line above which all these 6 components will be there, and after which the below the line the components with eigenvalues less than 1 will lying there. So it will, scree plot gives us a signal, that is which values are above the values, above the eigenvalues, above the eigenvalues like 0.1, and you have to choose up to that. This is a demarcation line to you, that is if you have to consider this number of components. So this is the thing, and the next, this is the idea of scree plot. And the next thing is component matrix. That means since there are the 6 component, first component, second component, these components are what? That is first components, which is explained the 29 point something we get earlier. The first components, look here, the first components, here the first components which explain the 29.358% of variance. Second components explain the 7.166% of variance. So in this component matrix, you get the 6 components in terms of the all variables. That means 6 variables. Look here in the first components, which variables are explained. You can choose from these variables, that is which variables are explained at what level. You can consider those variables, but the choice of the variables is far betterly can be done. That means among the 24 variables, how many variables we have to include in our models that for explaining the dependent variables in terms of their variability. Rotated component matrix gives us further better solutions. That is you have it is given that, look at this, it is arranging the values here. Look, variable 13. Now if I'm going to the Excel, that is what is the variable 13, that is the variable 13 is this, that is the closed drainage. It explains, it is considered as the most important factor to explain the socioeconomic variability of the model. So here the variable 30 is the most important, and from here 8, that means from this variability, this part, this one variable, this part, if you consider this part here, under this first component, the total variation holds 29 point something. That is what I get. In the under the second component, the variability is 7 point that's percent. So from here, which variables like 0.849, 0.833, 0.766, 0.728, And if there are any other variables, not other, you can choose these 4 variables from the first components, which are influencing your your data set in terms of their variability. Similarly, in case of second component, in terms of the second, which are explaining only the 7%, you can choose that is 8.234, that is variable 25, and 0.823 or 0.805. These 3 variables you can choose in terms of the variability, that is these are explaining our model in terms of the in terms of their variability. Similarly, from the 3, that is you can choose this 0.723, which in terms of the variability this is the highest. So by this way you can reduce the number of variables from the all list of 24 variables in terms of their variability. So this is the thing actually we are doing with the help of the PCA. So PCA basically, that means PCA basically, I'm just stop sharing. I'm just telling you what PCA actually doing. Just wait 1 minute. That it is actually lowering the number of variables, and gives us the importance of the variables in terms of where the variability level is highest. So in this regard, it is very, very helpful for the social science research, because to identify that which variables have the highest level of variability. There are different kinds of method. That is one important thing. First, you have to identify the eigen in terms of the eigenvalues, and then then choose the variables in terms of the eigenvalues greater than 1, and then how many components you get, and distribute and consider from the components the variables in terms of their level of variability. So this is all about. You can do one. You can take one example from any that is national level of data set. That is from where you have to choose that how many variables you have to select. So one questions probably it will comes, that is how I choose the level of significance. Is it someone questions, make some questions that how you choose the level of significance? That is, yes, it is. Is it anyone question? Is anyone make the question that how you choose the level of significance of these kind of things? Yeah. Look, when you do the sphericity test, we have if this is the questions, I don't get the thing. That is, if it is the question that yes, for the sphericity test, we have to do some specialized chi-square. So for the chi-square, the level of significance is not very that is different from our normal test of chi-square. That means you have to check the chi-square in case of 99% or 95%. So here in the SPSS, there is level of significance is considered as 95%. That means that is 0.05, and at that level, what is important to us, that is whether there is a pure sphericity, that is the null hypothesis. That is whether there is a pure sphericity, that means all the observations are equally variability, and the against the alternative hypothesis that not all the variables. So then we go for the Bartlett test, and the test is what you may ask the question that why it is chi-square. Then you have to go for pure statistical distribution of this that is correlation matrix, variance covariance matrix, and the number of variables. Actually, Bartlett's test is based on some correlation matrix values, and considering the number of variables, the value of the statistics is minus of n minus 1 minus 2p plus 5 by 6. That is, p is the number of variables into log of mod of the correlation matrix. So it is a chi-square with degrees of freedom p into p minus 1 divided by 2, that is the number of the variables, and it is tested against the level of significance at 0.05. So I think I have nothing to say further because it is already near about 2 hours. So if you have any questions or any problems, you can ask. Just you can. I will try to give you the answer. So if you have any problem or any questions.
Sir,